Okay, 10.2, hypothesis tests for a population proportion. So we're going to have three methods for testing hypotheses. The classical approach, the p-value approach, and then using confidence intervals. So first, let's look at an example that we can use to understand both the classical and the p-value approaches, because they're basically the same except for at the very end what you use to base your conclusion on. Okay, so a researcher obtains a random sample of 1,000 people and finds that 534 are in favor of the banning cell phone use, right? That would make more sense if that wasn't there, I think. Of banning cell phone use while driving. So, P hat is 534 out of 1,000. Does this suggest that more than 50% of people favor the policy? A majority, more than half. Or is it possible that the true proportion of registered voters who favor the policy is some proportion less than 0.5, and we just happen to survey a majority in favor of the policy? In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is, in reality, 0.5? So what is convincing or statistically significant evidence? Okay, when observed results are unlikely under the assumption that the null hypothesis is true, we say the result is statistically significant. So that's going to be an important term for us. When results are found to be statistically significant, we reject the null hypothesis. All right, so let's keep looking at this example. To determine if a sample proportion of 0.534 is statistically significant, let's build a probability model, because we might get a second random sample of 1,000 that would result in a different sample proportion, right? And we want to describe the variability so we can determine if the results that we obtained are unusual or not. So first of all, we've got to meet those three requirements for assuming it's normal, right? So n times p times 1 minus p, which in this case they've got worked out to 250. That's got to be greater than 10. Okay, and the sample size has to be less than 5% of the population size. So 1,000 is quite a bit less than 5% of the population. And they don't have it listed here, but they already told us that it's a simple random sample, right? A random sample. So that means we can use the normal approximation to describe the variability. So that means mu sub p hat is the 0.5, okay? And the standard deviation can be calculated using our formula. Okay? So now, if we draw that, here's what that would look like. Since it's approximately normal, we've got that bell-shaped curve with 0.5 here, and we would add 0.016, so this one would be 0.532, and subtract it 3 times. Okay, so now that we have a model, we can use it to look at the logic of these approaches to see if the majority of the population are in favor of banning cell phone use while driving. Okay, so first let's start with the classical approach. We may consider the sample evidence to be statistically significant if the sample proportion is too many standard deviations, and let's just say 2, above the assumed population proportion of 0.5, right? So, recall that our simple random sample yielded a sample proportion of 0.534, 534 out of 1,000. Okay, that means we can calculate our z value from our formula and see that it is 2.15 if you plug that in your calculator. So 2.15 standard deviations above the hypothesized proportion of 0.5. Okay, since this is more than 2, which we said that's going to be too far above the population proportion, we're going to reject the null hypotheses. There is statistically significant evidence to conclude that a majority of the population wants to ban driving while talking on a cell phone, right? We would reject the null hypothesis. So why does it make sense to reject the null hypothesis? If the sample deviation is more than 2 standard deviations away from the hypothesized proportion, okay, think about what that means. Okay, if the null hypothesis is true, that is, if the population proportion really is 0.5, then that would mean 97.72, basically 98% of all sample proportions should be less than 2, right? Okay, so if it lies in this blue region, then we're inclined to believe that it came from a population whose proportion is really greater than this 0.5, rather than to believe that it equals the 0.5, and we just happen to get one that lied in this region. Okay, notice though that our criterion for rejecting the null hypotheses will lead to us making a type 1 error. 2.28% of the time, so a little over 2% of the time. Okay, so if the sample proportion is too many standard deviations from the proportion stated in the null hypotheses, we reject the null hypotheses. And again, what do you call too many? Well, it depends really on your problem. Okay, they're going to tell us what we're going to think, but it depends on how important our problem is. And typically 2 standard deviations, that's quite a bit. Okay, a second criterion that we might use is to determine how likely it is to obtain a sample proportion of 0.534 or higher from a population whose proportion is really 0.5. So we could compute the probability of attaining a sample proportion of 0.534 or higher from a population whose proportion is 0.5 using the normal model. So what that means, let me get a pen in here. So what that means is really what we want to do is calculate the probability that p hat is greater than 0.534. Right? This is called the p-value. So what we're going to do is we already know from before, right, that our z value was 2.15. So that means we need to look at the probability that z is greater than 2.15. So if I'm looking on my chart, right, I'm going to look at 2.15 from my standard normal distribution chart, and I see it's 0.9842. Okay, but again, we're looking on a right-tailed test. So 1 minus 0.9842 gives us 0.0158. So we have a p-value of 0.0158. Okay? That means there's about a 1.5% chance that that value would fall in here. So once again, it tells us we're going to reject the null hypotheses, right? Less than 2 samples out of 100 would fall in here. Okay, and because that's unusual, for the most part, less than 5%, remember, we're going to say is unusual, then we take it as evidence against the statement in a null hypothesis. Okay, so what we want to take from this is that the classical approach is just looking at standard deviations, right? Just looking at standard deviations. And the p-value approach looks at probabilities. That's the difference between those two. All right, so let's actually physically do it ourselves now. Well, let's get a definition, I guess, first. A p-value is the probability of observing a sample statistic as extreme or more extreme than the one observed under the assumption that the statement in the null hypothesis is true. Okay? If the probability of getting a sample statistic as extreme or more extreme than the one obtained is small, okay, under the assumption that the null hypothesis is true, then we're going to reject the null hypothesis. Okay, so let's formalize a procedure for testing this. Now recall, the best point estimate of P, the proportion of the population with a certain characteristic, is given by this formula, where X is the number of individuals in the sample with the characteristic and N is the sample size. Okay. Also, if it's approximately normal, then we say the mean is P, right? And the standard deviation, we have a formula to follow, provided that these three requirements are met. So we got to think about these every single time. That the sample is a simple random sample, this calculation is more than 10, and the sampled values are independent of each other, they're saying here, but what that means is that the sample is less than 5% of the population. Okay, so to test hypotheses regarding the population proportion, we can use the steps that followed, provided that those three requirements hold. Here it is again. We've got our two-tailed, left-tailed, and right-tailed test, right? So we'll state our null and alternate hypotheses. Okay, note P sub naught is the assumed value of the population proportion. Then we're going to select a level of significance depending on the seriousness of making a type 1 error, or for our purposes, they're going to tell us a level of significance, right? Now, for the classical approach, actually the classical and the p-value approach, we're going to compute the test statistic. So that's our formula that we've used before. Note, we use P sub naught in computing the standard error rather than P hat. This is because when we test a hypothesis, the null hypothesis is assumed to be true. So we're assuming it's true and trying to prove otherwise, right? So then we can just take that as our value. Okay, so then here's the difference in our various tests, the two-tailed tests, the left-tailed test, the right-tailed test, and we would find the critical values, right, which we've talked about how to do. Then we're going to compare the critical value with the test statistic, okay, and if it falls in the two-tailed test either below or above, then we're going to reject the null hypothesis. And of course, in the left-tailed test, if it's less than our critical value, we'll reject it. And in the right-tailed, if it's greater than our critical value, we will reject it. Okay, now, p-value approach. Notice we do the same thing. We compute our critical value, same formula. We've got the same kind of test. The only difference is in the p-value approach, we actually compute the area under the curve, remember, and that's the probability of falling in that area, okay? Instead of just looking at our z value, we go ahead and do one step further and look at that probability. Or we could use technology, which we'll do an example of, and you've got the instructions in your technology tips from the text module. Okay, so then 5, this is for both of them. Step 5 is state the conclusion. Okay, on the p-value, if your p-value is less than alpha, right, then you're going to reject the null hypothesis. All right, now let's do one. Okay. In 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 stated they did not trust the media. At the alpha equals 0.05, 5% level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? Okay, so this problem deals with a hypothesis test of a proportion, right? Population proportion. And first of all, let's verify those three requirements. Is it a simple random sample? Well, let's see. It's a poll, so we'll assume simple random. All right, let me grab my pen again. Okay, N times P, and that's 0.46, right? Times 1 minus P, so what's that? 0.64? 0.54? Let's see. Yeah, 0.54. Let's see what that is. That is 250 point blah, blah, blah. So check. Okay. And we're talking about American adults, and we have a sample of 1,010. That's way less than 5%. So we can assume that this is normally distributed. Okay. So if it's normally distributed, then let's state our null hypothesis is that P equals 0.46. And our alternative hypothesis has increased. So we want to do P is bigger than 0.46. Okay, so that's step one. They have given us the level of significance, so we don't have to determine that. Okay, so if we're going to let's do the classical approach, and then we'll go back and review the p-value approach. All right, so I need my p hat. All right, so p hat is 525 out of 1,010, or 0.5198, let's say 0.52. Okay, 0.520 it rounds to. And let's compute our critical value, which is our test statistic, right? Z sub naught. Okay, remember our formula for that. We've got p hat minus p sub naught over sigma, which in this case is p sub naught times 1 minus p sub naught. So what did we say that was? 0.54 all over n, 1,010. All right, let me plug that in my calculator and see what we come up with. Oh, let me see. $3.83 rounded. Okay, so let's think about what this means. Okay, this is a right-tailed test, right? And we've got 3.83. We're way out here. And it asked us at a level of significance of 0.05. Let's look in our chart, okay? So this would be over here if I'm looking at 0.05 or 0.95. So either way, I'm looking in my standard normal distribution chart to try to find 0.05. Okay, because of symmetry, I can look also for 0.95, right? That would be the same thing since it's our right-tailed test, or 0.05, and instead of the negative, just make it positive. However is easier for you. So 0.05. Negative 1.645. Okay, so 0.05. Which means over here, I've got the same thing at, so what this means is any values we get for our test statistic that falls in this region, okay, then we're going to reject the null hypotheses. And our value was way over here. Okay, so our conclusion is there is sufficient evidence, statistically significant evidence, at alpha equals 0.05 level of significance to conclude that the percent of Americans that do not trust the media has increased since 1997. Okay, let's do the exact same problem, except let me try to find a color I haven't used that'll show up. Except let's do the p-value approach. Let's look at the difference in them. Classical p-value. Okay, the difference is very little. I still have the same proportion and the same z-value. Okay, the difference is now I'm going to use the z-value and look on my chart. Now I have the z-value, remember? Up here, when I was looking for my level of significance, I was looking for the z-value that corresponded to that level of significance. Here, I have the z-value, so when I look on my chart, oh, my chart goes 3.49 is 9998. So basically, resulting in this 0.9998, it's basically zero, right? Again, because it's right-tailed, I would do 1 minus 0.9998, okay, to find that probability. So that is 0.0002. Look how small a probability it is. So since the p-value is less than your level of significance, we would reject H sub naught and have the same conclusion. There is sufficient evidence to conclude the percent of Americans that do not trust the media has increased since 1997. So steps are exactly the same, process is exactly the same until I get to the bottom and decide, if I'm going to do the classical approach or the p-value approach. All right. Let's try that again. What do you think is more important? To protect the right of Americans to own guns or to control gun ownership? When asked this question, 46% of all Americans said protecting the right to own guns is more important. The Pew Research Center surveyed 1,267 randomly selected Americans with at least a bachelor's degree and found that 559 believed that protecting the right to own guns is more important. Does this result suggest the proportion of Americans with at least a bachelor's degree feel differently than the general American population when it comes to gun control? So it's telling us to use alpha equals 0.1 for our level of significance. Okay, don't forget we got to verify those 3 requirements first. It is a simple random sample. I think it said that up here. So yeah, randomly selected Americans. Okay, so N is 1267 times P times, that's the same P we had, isn't it? Yeah, so 1267 times 0.46 times 0.54 is 314. 314, so way greater than 10. Okay, so that checks out. And we're talking about adult Americans again, and 1,267 is way less than 5%. So the 3 requirements fit. We can use assume it's normally distributed. So let's get our hypotheses. H sub naught tells me that P equals 0.46. Okay, and H sub 1 is just do they feel differently, right? They don't want to say not is it less than 46%, not is it more than 46%, but they say it's not 46%, right? So we got a two-tailed test this time. All right. So we need that sample proportion, 559 out of 1,267. .441, 3 decimal place. We had 2 last time because it rounded to whatever it was, a 0 on the end, right? 3 decimal places for our proportions, though. Okay, let's do our test statistic. Okay, so we've got 0.441 minus 0.46, right? P hat minus P sub naught. So 0.46, 0.54 over N, 1267. Let's see what that is. Okay, I got negative 1.36. All right, so let's think about what that means. All right, negative 1.36. So we're like right here. Okay, alpha is 0.1. but this is a two-tailed test. So 0.1 divided by 2 is 0.05. Oh, hey, that's the same number we got to look at earlier. So I look in my table inside for 0.05. Okay, which we just did that one, and it was, what was it, negative 1.645. So that means right here, negative 1.645 and 1.645, that's our cutoff. Anything in here or anything in here, we would reject the null hypothesis. But we're negative 1.36, right? So this time there is not sufficient evidence at the alpha equals 0.1 level of significance to conclude that Americans with at least a bachelor's degree feel differently than the general American population when it comes to gun control. Okay, that's the classical approach. All you do is look for your Z value. Okay, and I find my level of significance gives me the Z value that I'm testing it against. Now, let's talk about the p-value approach as opposed to the classical. That means I want to find the probability. Hey, let's do that one on the calculator this time. So if I'm doing it on the calculator, I go into Stat, over to Test, and notice number 5 is one proportion Z test, right? So I'm going to click that. Okay, P sub naught is 0.46, so I'm going to enter that. X, that's the number of people with the characteristic, 559. N is your population. Okay, and then notice that you can choose whether you want a two-tailed test, a right-tailed, or a left-tailed. This is a two-tailed, so highlight that. And then you have two choices, calculate or draw. Let's first go over to draw and let you look at that. No, I've still got my box plots on, so I've got a box plot up there on top of it, but it will draw this for me. And notice what's down at the bottom. It tells you your Z value. It tells me this, right? And I got 1.3427 the calculator. Remember, these are rounding errors, but we better be very, very close. Negative 1.36 or 3427, right? Close enough. Okay, and it tells me my p-value also. So my p-value, it tells me, I'm going to write that right here, and that's what I'm interested in because we were doing the p-test. So there's my p-value. Remember, that's the probability of it falling in one of these areas. That's nearly 18%. That's not unusual, 18%, right? Less than 5%, that's unusual. So once again, there's not sufficient evidence to reject that null hypothesis. Okay, let's go back into the stat, over to test, choose that 5. Again, all your information should be in there. So let's just go down and do calculate. Notice what you get with calculate. It tells you your proportion statistic is not 0.46. Well, really, it's telling you what you're testing, right? That it's not 0.46. It gives you your Z value. It gives you your P, the 0.1794. It gives you P hat and the N. Okay, now be careful. Remember, all we say is we do not have enough evidence to reject the statement of the null hypothesis. This does not imply that we are accepting the statement in the null hypothesis, right? We're not saying that the proportion does equal 0.46. We're just saying we don't have enough evidence to say it's not. Okay. Also, be sure you understand that the p-value is the probability of obtaining a sample statistic as extreme or more extreme than the one observed if the null hypothesis is true. It does not represent the probability that the null hypothesis is true. Right? The statement in the null hypothesis is either true or false. We don't know which. Right? So that's not what the probability is telling us. So be careful about that. Okay. Recall that the level of confidence in our confidence intervals, right, represents the percentage of intervals that will contain the unknown parameter if repeated samples are gathered. So when testing our null hypotheses versus our alternative hypotheses, if a certain percent confidence interval contains P sub naught, do not reject the null hypotheses. However, if the confidence interval does not contain it, right, conclude that P does not equal P sub naught at that level of significance. Okay, so we've done a couple of examples of the classical approach and the p-value approach. Now we're going to look at confidence intervals. And we already know how to do confidence intervals. It's just how are we going to interpret them now for our hypothesis testing. A 2009 study by Princeton Survey Research Associates International found that 34% of teenagers text while driving. Does a recent survey conducted by Consumer Reports, which found that 353 out of 1,200 randomly selected teens had texted while driving. Okay, does that suggest that the proportion of teens who text while driving has changed since 2009? Use a 95% confidence interval. Okay, so first of all, we got to check those 3 requirements. And we had noted while we were reading, it said randomly selected. So let's look at N times P times 1 minus P. Let's see what that is. That's 269, so well over the 10. And we're talking about teenage drivers, so 1,200 in America is way less than 5%. So our 3 requirements are met. Now, remember from constructing confidence intervals that we had this formula. To get our upper and lower bounds, right? Remember that? All right. So I need P hat and I need Z sub alpha over 2. So P hat, first of all, let's get it. It's easy to get. P hat is 353 out of 1,200. So 0.294. Okay, now alpha over 2, okay, is, since we want a 95% confidence interval, let's think about what that means again. Okay, that means we want this interval where that's 95%. Okay, so that means that what's left over here is 0.05, 5%. So that's our alpha. So alpha over 2 is 0.05 divided by 2, 0.025. Okay, so that's what we're looking for, 0.025. Okay, so when I'm looking in my chart. Now I'm looking for 0.025 inside the body of the chart. Oh, have one exactly, right? Negative 1.96. So that means this is negative 1.96, and over here I have 1.96, right? Okay, so if I plugged those into here, my p hat and my 1.96 in here, I would do a plus and a minus, I would get my bounds. Or we could also do that confidence interval on our calculator, right? Here's the formula, here's what I need. Or on my calculator, let's go into Stat, Test, all the way down to A, right? All the way down to A. Okay? Because it's a confidence interval. Yes, it says one proportion Z interval. All right, X is 353, 1200, 0.95, and let's calculate. And it tells me either by plugging into my formula or my calculator, and I get 0.268 to 0.320. So 0.32, 31995 is what I got. Okay, so 0.34 is not in this interval, right? Because 0.34 is not in the bounds of this interval, there is sufficient evidence to conclude that the proportion of teens who text while driving has indeed changed since 2009. Okay, so that's the confidence interval method. Think about this. This is interesting. I found this really interesting. That same Consumer Reports article cited that 75% of teens have friends who text while driving. Now notice 34% of the teens they surveyed said they texted while driving, but 75% of their friends text while driving. So think about what that says about the difficulty in finding truthful responses to questions while conducting a survey. Remember those first issues we talked about in this course? Yeah. Okay, for the sampling distribution of p hat to be approximately normal, we require this to be at least 10. What if this requirement is not satisfied? Okay, remember we looked at this before, but what about for hypothesis testing? Okay, we stated that an event was unusual if the probability of observing the event was less than 5%. This criterion is based on the p-value approach to testing hypotheses. The probability that we computed was the p-value. We're going to use this same approach to test hypotheses regarding a population proportion for small samples. So the p-value approach, if your sample is small and a little bit different. All right, so let's look at one. In 2006, 10.5% of all live births in the United States were to mothers under 20 years of age. A sociologist claims that births to mothers under 20 years of age is decreasing. She conducts a simple random sample of 34 births and finds that 3 of them were to mothers under 20 years of age. Test the sociologist's claim at the alpha equals 0.01 level of significance, 1% level of significance. All right, so we got to meet those 3 standards, right? So N times P times 1 minus P, which is 0.895. Let's see what that is. Uh-oh, that's 3 point da da da. All right, I cannot assume this is normal then. If I can't assume it's normal, I'm going to use instead the binomial distribution function, right? Not the normal distribution function. So remember back from, I don't remember what chapter, but a good ways back, we had the binomial distribution where we just talked about successes and failures, and this will fit. Either yes, they're under 20, no, they're not. And we had that formula, let's see, for the binomial distribution function, where we're finding the probability. Now remember, that's why we're doing the p-value, because the p-value is we're finding the probability. Okay, and we had this as a formula. Remember the tree diagrams? And this was the formula. And so, let's think about, try to put this together with what we would need here. Okay, so this is what kind of test? Okay, so births to mothers is decreasing, is going down. So let's get our hypotheses. That'll help us. And okay, so it's a left-held test. Okay. Now, what we would need to do, this is that 3 of them, we want to know the probability that x is less than or equal to 3. And x, remember, let's let x be the number of live births to mothers less than 20, right? So because we have 3 out of 34, we have p hat is 0.088. Okay? Now, what we really need to do to test this, though, less than or equal to 3, we really would have to find the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. Right? That would be the same thing as the probability that x is less than or equal to 3. And so we have this formula here that we could plug that into. We know our n, we know our x, and we know our p, or we can plug it in the calculator, right? So that's what I'm going to do. But I wanted to go through all this instead of just strictly plugging it into the calculator and remind us and refresh our memory. Oh yeah, remember when we were doing the binomials? Okay, so if we are going to plug this in the calculator, okay, we want to go to distribution. So that's second var, right? To get into our distributions. And then I'm going to go down to the binomial cumulative. So CDF, binomial cumulative. Okay, N is 34. P is 0.105, right? Not P hat, P, right? What we're testing, 0.105, and 3 are successes. And we get, this is 0.51. Okay, so now this p-value is greater than my level of significance, so we do not reject the null hypothesis. there is not sufficient evidence to conclude that the percent has decreased below 10.5%. Okay, let me know if you have any questions.